students, welcome back. This is Torres, Elbow Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need something, please send me an email and I will do whatever I can to try to help. So lucky you, you get to hear my voice for another lecture. But the best part is we're going to be doing another example on how to use the 4 steps of hypothesis testing when you have the population mean and the population standard deviation. Yay! So here are the 4 steps to hypothesis testing. Let's talk about each one just as a brief review. The first step is to write your hypotheses. You're going to write your null hypothesis, which is the one that describes the status quo, what we expect in the population, and you're going to write your alternate hypothesis. The alternate hypothesis addresses the question. Whether you're working with proportions or you're working with means, you're going to use the notation that describes the population parameter. The next step is usually the longest step, and that is the prepare step. So during the prepare step, you're going to do a variety of things. You're going to choose the significance level, and you're going to find the test statistic for that significance level. To do this, you will also need to decide whether you need a 2-tailed or a 1-tailed test. And if you need a 1-tailed test, do you need a left 1-tailed test or a right 1-tailed test? You may have to calculate the standard error for your sample during this time as well. You might also need to check the assumptions to make sure your data is normal. So unless something is already stated in the problem that tells you to assume normality, then you would have to check for the conditions of the central limit theorem. This is also the time where you want to make yourself a model and establish the area of rejection and the area of retention. The next step is the compute to compare step. In this step, you are going to calculate your Z obtained using the sample information, the population information, divided by the standard error that you calculated for your sample. Once you calculate your Z obtained, you will compare it to the test statistic that you got in the prepare stage, which is called the ZCrit. And also, you're going to compare it with the model that you created. If your Z-score falls in the area of rejection, this is evidence that the null should be rejected. Also, this is the time where you will calculate the p-value for your test statistic, for your Z obtained. If the Z obtained's p-value is less than your significance level, or your alpha, then you should reject the null hypothesis. It's important that your obtained Z falls in the area of rejection, and also your p-value is less than your alpha. If you get mixed results, something went wrong. In the last step, you're going to decide whether you will reject or whether you will fail to reject, in other words, retain the null hypothesis, and you state your conclusion in the context of the study.
So in this video example, we're going to be talking about dinosaur bones. It says, humerus bones from the same species of animal have approximately the same length to width ratios. It is known that species A has a mean ratio of 8.5. Suppose 41 fossil humerus bones were unearthed at a site where species A is known to have flourished. We assume that all bones are from the same species. The length to width ratios of these bones have a sample mean of 9.26 and a sample standard deviation of 1.2. Can we conclude that these bones belong to species A? Test with a 5% significance level. So I have copied the information into Ziteboard. Remember, Ziteboard as well as the Google Slides are linked in the description box below. Another thing you'll find in the description box is a document with common significance level ZCrits and also the normal distribution calculator that we found for free online. So I'm going to go ahead and read the problem one more time. It says, humerus bones from the same species of animal have approximately the same length to width ratio. It is known that species A has a mean ratio of 8.5. Suppose that 41 fossil humerus bones were unearthed at a site for species A is known to have flourished. We assume that all bones are from the same species. The length to width ratios of these bones has a sample mean of 9.26 and the sample standard deviation is 1.20. Can we conclude that these bones belong to species A? Test with a 5% significance level. Okay, first things first, I've got to write my hypothesis. So here we're talking about a mean ratio. Okay, we're not talking about a proportion or a percentage. So I need to think about my H0, which is going to state what we see in the population, and we're using mu because this is regarding a mean. H0 is going to have what we see in the population. So we're going to have mu equals the mean ratio of 8.5. Okay, because that's what we're expecting for species A to have. Okay, now with these new bones that we found, we want to know, is there a chance that these bones are different, are going to have a different ratio, significantly different ratio than what we see in species A? If it's really different, then these aren't going to be bones that belong to species A. They might be bones that belong to something different, or it could just be like a really random one-off of bones for that species, right? We're never really going to know for sure. We can use statistical probability to have some idea. Since we're looking for just a difference, any difference, we're going to have mu is not equal to 8.5. So, hypothesis, H0, mu is equal to 8.5. Alternate hypothesis, mu is not equal to 8.5. Awesome. Okay, so the next section, we're going to go ahead and start to prepare. By doing this, we want to make sure we list as much information as possible so we don't have to keep going back into the question. We want to choose our significance level, our test statistic. In this case, we're going to be using a ZCrit. We want to check any requirements, state assumptions, create our model, etc. So right here we have that the mean ratio, right, the population ratio at this time is believed to be 8.5. Okay, that's the information that we have about species A bones. We have 41 bones, right? So suppose that 41 fossil humerus bones were unearthed. So the sample size is 41. And for these 41 bones, they found that the sample mean was 9.26, and the standard deviation for the bones is 1.2. And we want to know, can we conclude that these bones belong to species A? Test with a 5% significance level. Okay, so our alpha is going to be 0.05. Next, we need to know what kind of test we need so we can find the ZCrit. So since I'm looking for any difference, I'm looking for values that are much, much lower than 8.5 or much, much higher than 8.5. So in order to do this, I need a two-tailed test. Okay, so for a two-tailed test at a 5% alpha, I can go up to my common significance levels. As a reminder, a link to this graph is in the description box below, and I can go to two-tailed test, two-tailed z-test. 0.5 is going to give me plus or minus 1.96. So my ZCrit is going to be either positive or negative 1.96. All right, so let me start to draw out this information. Okay, so I've got my normal curve right here. I'm going to go ahead and set up my z-scores, 0, 1, 2, 3, negative 1, negative 2, negative 3. Scoot this up a little bit. And I'm going to go ahead and start setting up my model here. This is going to be the information for this population. Yeah, we're going to have 8.5 right here. And we have to calculate the standard error that is going to be here. Okay, now this one's a little bit unusual because it gave us the sample standard deviation instead of the population standard deviation. For the sake of this example, let's go ahead and use the standard deviation of the sample to figure out the standard error. Okay, so to figure out the standard error for means, I'm going to use the standard deviation divided by the square root of the sample size. So my standard deviation of this sample was 1.2, and I'm going to go ahead and divide that by the square root of 41. So I can get my Google calculator here and figure this out. So if I can adjust this just a little bit more so that it will all fit. Okay, I think that'll be close enough. All right, so I've got 1.2 divided by the square root of 41. And I get that my standard error should be 0.187. So I'm going to get my standard error is 0.187. And I'm going to go ahead and just round that up to 0.2, quite a bit of rounding, so that I can continue to make my model. Okay, this distance right here is going to be 0.2. So 0.2 plus 8.5 is going to be 8.7, plus another 0.2, 8.9, and then another 0.2 is going to be 9.1. And if I go in the opposite direction, I'm going to get 8.3, 8.1, and then minus another 2, I'm going to get 7.9. Okay, awesome. I can also start to mark my ZCrit. I'm going to go ahead and mark that in this blue color. My ZCrit on one tail, on the right tail, is going to be positive 1.96. So my ZCrit is right about here. That's positive 1.96. So if I get any values that are in this area, z-scores in this area, then I'm going to go ahead and reject. Okay. And then the other area I'm going to mark off, the second area in my two-tailed test, is negative 1.96. So it's going to be right close to right here. This is negative 1.96. Everything that is less than that ZCrit, I'm going to also reject. So the area that I will use as my area of retention is going to be this area right here, between negative 1.96 and positive 1.96 will be my area to retain. Okay, so if I get any z-scores that fall through here, I'm going to be able to retain. Now again, I want you to know that I rounded this. So right here, this is not really 0.2. I rounded it, and I'm going to go back to not rounding it so we can reduce the error a little bit. But I just wanted to go ahead and make the model as best as I could, so I had some idea of what was happening. As the next point, what I'm going to do is go ahead and compute the test statistic. In this case, I'm going to compute the z obtained, and I'm going to find the probability or the p-value of that p obtained. So first things first, let's get this calculated. So my z obtained, I'm going to do this pink, z obtained is going to be my sample mean. And from that, I'm going to subtract the population mean, and then I'm going to divide that by the standard error. So let's put the values in here. My sample mean is 9.26. My population mean is 8.5. And I'm going to divide that by my non-rounded standard error, because I want to make sure that I try to decrease error as much as possible. Okay. So I'm bringing over my Google calculator, and we're going to go ahead and start computing. So 9.26 minus 8.5 equals, divided by 0.187 equals, and I get that my z obtained is positive 4.06. Awesome. All right, next thing I need to do is I need to calculate the probability or the p-value of getting a z obtained. So the fancy way of writing that out is the probability of z obtained being equal to 4.106. I'm going to go ahead and go here to a probability calculator. So this one's a little bit different than the one we used the last time. It still works. You need to, make some decisions about which one you like the best, but I like to give you options. So my z-score here is positive 4.06. I'm working with a 5% significance level, and I'm going to use a two-tailed test. So now I'm going to calculate. And if you see here, what's really nice about this calculator is it will tell you the exact p-value, and it will tell you if your result is or is not significant. So right now it's saying my p-value is 4.09 and the result is significant at p being less than 0.05. So it is significant. So I'm going to go ahead and go back to my Ziteboard. The probability of getting this p-value is 0.000049. So this is, definitely looking good. Okay, so now I need to compare where my z obtained falls on my model. So here is 0 z-score, 1, 2, 3, 4 is all the way out here. So 4 z-score is going to be all the way out here. This is a z-score of positive 406. So it falls in the area of rejection. For the p obtained, or the probability of the p obtained, I want to compare this to my alpha. Well, my alpha was 0.05. If my alpha is more than my p-value, then what this is telling me is I was willing to risk a 5% chance of creating a type 1 error, and this is telling me that I'm likely to commit a type 1 error 0.000049 probability if I reject with a z-score of 4.06. So this is also telling me reject. So I'm just going to write right here, alpha is greater than p-value, reject. Okay, if alpha was less than the p-value, then you're going to retain. Okay, the last part is that we want to interpret the information right here, interpret, reject, or fail to reject the null hypotheses, state the conclusion in the context of the study. All right, so at this point, we are going to make a decision to reject, right? Everything is telling us to reject. So here's my black pen. We are going to reject the null. Okay, and in essence, what this is telling me is that by rejecting the null, the dinosaur bones that we found are different than what is expected for species A. So what this can tell us is either this is a completely different species, or by chance, species A happened to have a gibungous version of that species. Like he was just like the gigantic one of that species. It's not normal. He was just this randomly large species A. So it can't tell us for sure, but right now it was definitely bigger. So it's one of those possibilities. Either it's a humongous species A or it's a completely different species. So let's go back and reread the question. Humerus bones from the same species of animal have approximately the same length to width ratios. It is known that species A had a mean ratio of 8.5. Suppose that 41 fossil humerus bones were unearthed at a site where species A is known to have flourished. We assume that all bones are from the same species. the length to width ratio of these bones have a sample mean of 9.26 and the sample standard deviation of 1.2. Can we conclude that these bones belong to species A? Test with a 5% significance level. As I look at this, I notice that species A has a mean ratio of 8.5. So that's going to be the population mean for the humerus bone. The sample size was 41 humerus bones, and when they took the average ratio of these sample bones, these 41 sample bones, that mean ended up being 9.26, and the standard deviation was 1.2. So in writing the null, we needed to make sure that we wrote the null according to the population. So since we were dealing with means, we were going to use the notation we were going to use the mu notation, and we were going to use the population mean in the null. So since the population mean was a ratio of 8.5, that's what we're going to use here. For the alternate hypothesis, we're going to have the same information, mu. This time, we were looking for any difference, right? The researchers wanted to know if this was within what was expected, or if this was substantially low, or if this was substantially higher. So since we were looking for any difference, we decided to use the not equal sign to demonstrate that we were looking for any difference. Now, one important step that I actually skipped in this video was checking the sampling distribution's conditions, right? So using the central limit theory to have some indication, some evidence that this sample was normally distributed and therefore suitable for statistical use, right? So we don't have evidence of that. However, assuming the distribution is normal, okay, assuming it met the conditions, then the rest of the prepare phase really looked at having you write out the given information. So for example, we knew that the population mean was going to be 8.5. We knew that the sample size was 41. The mean of the sample was 9.26. And the standard deviation was 1.2, right? All that information was given. We were asked to use an alpha level of 0.05, so 5% alpha. And because we were looking for any difference, and we wrote the null hypothesis and the alternate hypothesis already, and we know that the alternate hypothesis was not equal to, therefore, any difference, we're looking for values that are extremely low or values that are extremely high. That tells us we have a two-tailed test. We looked up the ZCrit, right, for a two-tailed test at 5% alpha, and we found that there are two borders. There's the lower border, which is negative 1.96, and the upper border, which is positive 1.96. We've marked off those borders, and we sectioned off areas of rejection. So right here we had positive 1.96, and everything greater than that was going to be an area of rejection. We also found negative 1.96, and everything underneath that was going to be an area of rejection. And everything in the middle here was an area where if our Z obtained fell in this area, then we were going to go ahead and retain. So we marked off our model. We also created this model so that we were ready to go. We found the standard error. This time we used the standard deviation of the sample, right, because that's what was given. We decided to move forward with that. And we divided it by the square root of the sample size. We found that the standard error was 0.187, but to complete our model, we went ahead and just rounded it to 0.2. So I completed my model here, and I have a very clear indication of where the theoretical raw scores that align with the anchor z-scores are here, right? So I'm getting an idea of what's happening. Okay, so for the next step, I'm going to go ahead and compute my z obtained and compare that to my ZCrit, and I'm also going to compare the probability of getting that z obtained to my significance level or my alpha. So Here in this section, I went ahead and plugged in the values. So for my sample mean, I plugged in 9.26. From that, I subtracted the population mean, which was 8.5. And once I found that difference, I divided it by the non-rounded standard error of 0.187. At that point, I found that my Z obtained was positive 416. That was in the area of rejection, so I went ahead and rejected. I used technology to find the probability of obtaining a Z-score which was equal to 4.06, and it said that the probability of obtaining a Z-score that was 4.06 was 0.00049 probability, right? Very, very small probability. So we're going to go ahead and reject because the alpha, which was 0.05, is more than the p-value, which means that I was willing to risk committing a type 1 error at 5% alpha, and because my z-score is so high and the probability of getting a z-score that high is so low, the probability of me committing a type 1 error is 0.00049. So I'm going to go ahead and reject. Finally, I'm going to go ahead and state my conclusion in the context of the study, which was the findings of the z-test suggest that the mean of the 41 bone sample is statistically different than the expected mean of species A dinosaur bones.
So what's the big idea? The big idea is that the 4 steps of hypothesis testing provide a systematic process to answer a research question concerning the population parameter. The 4 steps are hypothesis, prepare, compute compare, and interpret. So that's it for today. Don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay, this is your teacher Torres saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!